Okay, so the first, I will just start formally. So I will go to this first topic, and part A will be the formalism of local spaces. And I will consider a smooth curve over some ground field, K, and the Hilbert scheme of points in C. So it's graded by the length of the scheme. And this moduli of points of length n is just the symmetric power of the curve. So I will complicate things a little bit by choosing some set I of colors, and then I will look at the Hilbert scheme of the multiple of the curve. So it's curve with various colors, and choosing a subscheme here means choosing a subscheme in each copy of C. So this is the Hilbert scheme to the ith power. And then this degree decomposition gives a decomposition here according to alphas, where alpha is a formal combination of elements of this set I. So it is non-negative integral combinations of I. And this H alpha C itself, what it is it's a product over the colors, and then one has a symmetric power of the curve to the multiplicity of I in alpha. Okay, and now I can say what I mean by an I-colored local space over a curve C. So this will mean a space which lives over a colored Hilbert scheme. So whenever I have some element here, so what is this? It's a system of subschemes, one for each I. So, okay, I can write it formally as some DII. So for each such guy, there will be some fiber here. And besides this structure map, I will also need one more piece of structure, consistent system of isomorphisms. So isomorphisms will depend on two subschemes, and we will ask that these guys are disjoint. So they lie in this colored Hilbert scheme. And isomorphism will compare the fiber at these two subschemes with the fiber at the disjoint union of subschemes. So I will ask that it is strongly disjoint, meaning that even if so the colors will not save you if there are repetitions into. Okay. And so one asks that one has such consistent system of isomorphisms, and one can say that such structure is weakly local if iota is just an embedding, so not quite an isomorphism. Okay. So let me just introduce some kind of particle terminology. So if I take a point in the curve in some color, I can look at this colored point, which lies in the colored Hilbert scheme, and I look at the fiber here, and I will call it particle I at the point A in the curve. And then the regular part of the Hilbert scheme will be the part where one takes these colored subschemes, which are just sets, and di are disjoint. So there are no multiplicities whatsoever. So then, if I take a d in this regular part, then locality asks that the fiber at D is a product over all points that appear in D. So here, because it is just a subset, not a subscheme, then we can think this way. And so therefore this regular part sort of so Z restricted to the regular part, you can think of as configurations of these I particles, I many particles on the curve before they meet. And then for general D, so here you can think of ZD as some kind of collision of particles as one approaches D by some D primes which are regular. Then this product of particles, so Z of D prime is a product of particle spaces. Spaces converges to some fiber which can be more interesting, maybe, say, for instance, not a product, but something more complicated. So what are examples? So the basic example is the loop Grassmannian of Beilinson and Drinfeld. So if I have some algebraic group G, then the loop Grassmannian will be here described as a space over the Hilbert scheme, and the fiber at some finite subscheme will be, well, we can think of this as cohomology on the curve supported at this finite subscheme. And so what this means is that these are pairs of a G torsor P on the curve, say, let me say T, and tau, which is a section of this torsor, in other words, a trivialization, but not on the whole curve, but away from this divisor. Okay. This is somehow a local space, because if this disjoint union of two things, then the local cohomology happens independently at these two guys, so we get a product. Okay. And so this is sort of the simplest example, but this one has more structure, a factorization structure. But so somehow the first example of this kind is in Finkelberg, Shechtman, treatment of quantum groups via vanishing cycles. And since then, there are many examples. So another example will be a formulation of an idea of Kamnitzer-Knudsen. And the idea is that one takes some K algebra A, take a module, and then define Grassmannian of the module for A to simply be all submodules of these modules. Okay, submodules. Okay. And, but the idea is to probe this with finite schemes. So this will create a version of the Grassmannian which, say, is related to a curve, and it will map to the Hilbert scheme, and the fiber at subscheme D will be again the same idea, but one will change the algebra and change the module. So by implementing this D. So AD simply means that one pulls back this algebra to this scheme. So it is A tensored over the field with functions here and the same there. Okay. And they were thinking of this in the context of representations of the generic representations of the pre-projective algebra of a quiver, but somehow one can think of this as some construction of a local space, because again, pulling back a module to a disjoint union of two schemes is just sort of independent business with respect to these two components. So this is local. Other examples. Okay, so now some abstract example. So there is a functor from weakly local to local spaces. I will denote it like this. And this will be a subspace of Z, and we will think of it as the local path of a guy Z, which is not quite a local space. So the structure maps iota are inclusions rather than isomorphisms. And this local path will have the same particles. And so now it's clear how to define this guy over the regular part of the Hilbert scheme. So the fiber at some colored subset is just as the formula that we used above. So it's the product of all z AIs, fibers at points. So I have a curve here, maybe several copies of this curve, c times I, c times j, and I have here some points AI and BI and CJ, and D contains several of such points. And so I take all points, all colored points which appear in D. So this is what we should have if the space is to be local. But this is a good definition only when D is regular. And then there is a good thing about weakly local spaces, that this product lies into Z of D. So the weak locality iota forces this product to be embedded here. Okay. And so this whole thing, therefore, lies in Z. Sort of this local part lies in Z. And the local part that I was able to define. And so now I can take the obvious idea which everybody uses, for instance, Misha Finkelberg, and that's to take the closure of the part that you can define inside this big space, which is not so good. And then, since this regular part satisfies locality property by continuity, it will be true everywhere, and we will get some local space. So there is a great ease in defining it, and one pays because it's hard to calculate closures explicitly. Okay. Okay, so now one example of this. If I have some local space, then a vector on a vector bundle V over this, a structure of a local vector bundle is sort of like we do it on spaces. So on spaces I have ZD prime, ZD second, and their product is the fiber at the disjoint union. So I can restrict vector bundle here on each of these spaces. And since this space is a product of these two, there is a possibility that, that the vector bundle restricted here is the tensor product of vector bundles. And so a locality structure for a vector bundle is therefore, again, such consistent system of isomorphisms. So we will see in examples in a moment, but the puzzle is now if one takes the projective space of this local vector bundle. So vector bundle was over Z, it is still over this local space. and so it maps to the Hilbert scheme. And so the question is whether this one is also local. Okay. So in order to be local, it should have property somewhat like this, that the fiber at d prime, so what do I, okay, the fiber at d prime times the fiber at d second is the fiber at the union. So we want such isomorphism. So what does this mean? Since I'm calculating the fiber in stages, so it means that I will restrict my vector bundle to the fiber of z at d prime, restrict it to the fiber at d second, and so on. And so now I would want an isomorphism here, but it's clear that there is no such thing, but there is Segre embedding, because this is a tensor product of these two. Okay. And so this is therefore, so this guy is a weak local space. And then we can just take P loc, the projective space in the category of local spaces, and it will mean that I take projective bundle and then its local part. And this will be the main construction of such spaces for us. So now I can define Zastava spaces. So now I want to use my one and only trick to construct some local spaces. So the first thing is that if I take Z to be Hilbert scheme itself, it is a local space, a trivial one. Okay, so now if I would have a vector bundle here, I could take this local projective space and get a local space. But what I know here are not so much vector bundles, but one knows all local line bundles. So these data are standard in the Beilinson and Drinfeld theory, and we will get a local line bundle depending on some data. And the data are one line bundle on the curve for each color, and also matrix integer valued of I times I type and symmetric. And how do I get this local line bundle? So let me just call it L. So what is it going to do on some connected component of the colored Hilbert scheme? So the connected component itself is a product of symmetric powers, one for each color. And in this space, we have discriminant divisors. So Dij, where I and j factor have something in common, or where I factor has multiplicities of points. Okay. So there are multiplicities up here. One can think, one can cover this whole thing with a large power of C before symmetrization, and then one will have ordinary diagonals delta A, B, corresponding to points in A. And then these guys are images of these diagonals. Okay, and now what one does here is this is a product. One can take out a tensor product of copies of line bundles, but I have to put it on the symmetric power, so I have to do some kind of symmetrization to put it on this power. So this is how I can get a line bundle here. And it's a local line bundle, but it's not very interesting. So what is interesting is that one can modify it, twist it by using these divisors, and one with some multiples which are given by this matrix Q. Okay, so one just modifies along the diagonals, and these are just all local line bundles. And actually, things will simplify. I will just ask that all Li are trivial, because local line bundles are locally trivial, and I'll be only interested in local geometry, what happens locally on a curve. So I will have one line bundle associated to a quadratic form. Okay, so I know all local line bundles on this trivial local space. So what I will do is not go to a more sophisticated space. I will stay on the same space, but I will produce a vector bundle by using the following diagram. So I will have here one copy, and here m copies. So what this will contain are objects of the following type. So I will have some finite, some subscheme, and then I will have a filtration of length m of this filtration. And then one can project to a single copy here and to F1, Fm here. Okay, and oh, Fm is the moduli of such things. So there is some finite subscheme and the filtration of length m. And so call these maps P and Q, these projections. And so now I can take my line bundle, which is a local line bundle, and I can pull it back by P and push it forward by Q. And since Q is some finite map, this will be a vector bundle of finite rank. So call it, say, VQ, and I will also have this M as a parameter. And now this is almost a map of local spaces, and and whatever it is, it suffices for this to be a local vector bundle. So what does this mean? Say, what is the fiber at some subscheme?
With these regular, what do you get?
So let me say first in general. So what this is, it is global sections over all filtrations of D of line bundle at each of these subschemes. Okay. So I have omitted something. To start with, I should be on this power, so I should take the exterior env power of the line bundle, right? And then this is the correct formula. Okay, so the same line bundle, yes. So now let's see what happens at a point. So if I have a colored point, then I have filtrations F1 up to Fm of a colored point, the space of such, and all such filtrations look like empty, 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 then it jumps to the point and remains a point. And so there are kind of n+1 places where one can jump from empty to A. Okay, and here I should take sections of, sorry? I is a color. So forget the color, and so truly I should have AI everywhere. Okay. Okay, and so here we have a tensor product of some lines, so it's a line, and so it is k to the n+1, and that's what happens at a point with the vector bundle. Sorry, does it make sense? So this is a set.
Yeah, but I mean, it's L. It's not canonical. It's M+1 dimension, but it's different, right?
Right.
L to different powers. L
Yes.
different powers.
Yes. Right. So anyway, once I have my local vector bundle, out of it I can cook a local space. I take projective space of fibers of this vector bundle, except that I should, as usual, take the dual, and this is what I will call the Zastava space for parameter M and Q. So more precisely, somewhere here I also have this I. And this will be something over the Hilbert scheme, and it will be a local space, but because we had local vector bundle and the local path of the projective bundle. So then again, the question is, what is it at a point? So what is this Zastava space at a colored point. So it's the projective space of this Km plus 1. So this is Pm. And then back to the Dennis's question of what is canonical here. This Pm will be the symmetric power of the P1, which is the fiber when M is 1 at the point. Okay. And when M is 1, we get P1, and its symmetric power is, you just look at this formula and it's immediate. Okay. Okay, and so in this way we get many local spaces. We know there are that all particles, remember there is one particle for each I, and maybe it could even depend on the point, but all particles are just the same. Okay. Okay. Okay, so I can take more liberties and I can define a loop Grassmannian for this data. Maybe I'll write it like this. And the way it's done, it's some kind of limit of this system of spaces. And so it means that I will take the inductive limit of, so I need to, so this is again some space over the Hilbert scheme, or colored Hilbert scheme, and the fiber at some D, we will just take this Zastava space and its fiber at D, but I will allow D to grow by multiples. And as it grows, this space, it turns out, it grows. So we just get some kind of a union of these guys. Okay. So the claim is, I think, something like this, that if D prime lies in D, then the fiber of M filtrations at D prime lies in the fiber of M filtrations at D, sort of the bigger subscheme has more filtrations, right? And so then it just goes through that. So all filtrations, it's just a subset, right? Okay. But then I have dualized somewhere, I hope. Yes, you're right. And okay, but this is still just kind of half of the loop Grassmannian. So this is what is in the theory of loop Grassmannians. It's a closure of one semi-infinite orbit. So this is the kind of semi-infinite orbit for closure of the orbit for this data. And then one gets formally the whole thing by some kind of shifts, and this shift means that one multiplies with the group generated by I and takes some kind of a quotient with respect to semi-group which acts here. So one just enlarges this space by how much this is larger than this. So by adding, going into some negative directions in each component.
I know S0 bar, what does S0 bar M mean?
Oh, I just, if this is the mth Grassmannian, well, it did depend on M.
Yes, but I mean,
Oh, sorry. So intuitively, it's just, so intuitively at least, this should be a closure of the semi-infinite orbit in the loop Grassmannian of a reductive group. So, okay. For m equals 1, yes, okay. So for m equals 1 and good choice of Q, okay. Yes, there are. Sorry. Uh-oh. And so this is about it for this first section, this construction of local spaces, which I call zastavas, associated to such data. And we will later relate to usual loop Grassmannian and usual zastava. Okay, so maybe one more comment, since I said that it's hard to calculate. So the only thing that we ever did is take some closure in this projective bundle of regular local path. So when D is regular, then the fiber was a product AIs of projective spaces. Okay, and this embedded into projective space of the fiber at this divisor by Segre embedding. And so this Segre embedding, we can, if we think of equations for this embedding, then we can call them locality equations, because this is the local path. And so now the question is, what are these locality equations? So in some limit, there is some limit of these locality equations as one passes through this this limit here, and one gets equations for embedding of this funny loop Grassmannian into some huge projective space, and this will and these locality equations now are equations for this big embedding, And so locality equations, which were algebraic, here when we dealt with finite stuff, under all limits, they become differential equations. Okay. As everything concentrates on formal neighborhood of some subscheme. And these differential equations are a generalization of KP hierarchy. Okay, as we'll see. Okay. So in the cases when one such guy really corresponds to an ordinary loop Grassmannian, the embedding equations are known to be KP hierarchy equations. And so here we are just interpreting KP hierarchy as limit of some kind of locality equations. Okay. So I don't know whether such interpretation is known or not. Okay, so I have.
So the fact that for m equals 1 and capital M Q being the Cartan matrix to recover neutral Lasalle, it's a theorem.
Yes.
And it's not immediate, right?
I will comment in a moment, yes. Okay. Okay. So now I want to recall what are these Zastava spaces usual. So using classifying spaces. And this part just comes from my unsuccessful attempt to recall Zastava spaces in Drinfeld seminar. So now I'll try to make it in a more reasonable way. And so the idea is, for instance, if one looks at the loop Grassmannian, the fiber at some subscheme, so we talked about it here. One can think of this as a map of pairs. So curve minus D going to the classifying space of the group and to the point. And now the map from curve to the classifying space, this is a torsor. The map to a point has no structure, but the compatibility of these two is a trivialization of T on U. And if I go to a version of loop Grassmannian, which Dennis considers, called the global loop Grassmannian, which is something like inductive limit over, over subschemes D under inclusion. So here I'm just gonna remove somehow this extra data D, and in this case we have maps from the curve here, the generic point, to the same data. Okay, and here, and so now I can think of this pair as a classifying space for this moduli, which is the loop Grassmannian, and this can be implemented in various ways. So what do I find in the loop Grassmannian? We know that in the loop Grassmannian, the torus fixed point for a Cartan here is the loop Grassmannian of a Cartan itself. And then if I take fixed points on the rotations, so this is the copy of the multiplicative group which rotates loops, then this will be identified with co-characters. And let me just denote it this way. And when I have these points in the loop Grassmannian, I can use them to generate orbits, like, say, G lambda will be a disk group orbit of L lambda, S lambda will be a loop group for the unipotent radical orbit. There will be also a negative version where one has the opposite Varel. And intersections of these orbits have some meaning. Irreducible components of intersections give canonical basis in the representation theory of the dual group, so some kind of canonical basis. And so this is one of the reasons to consider these guys. And the Zastava spaces will have to do with considering intersections of these two. But we want to think of this all in terms of classifying spaces. So let's see, the closure of one semi-infinite orbit, so orbit of this type, can be thought as the loop Grassmannian with some condition. So let me just introduce in general loop Grassmannians with a condition. So Y will be a G space which contains an orbit which is open dense. And then this can be defined as maps from. So again, if I want to phi bet D, C minus D, and now I have some analog of this pair, and this analog will be the quotient, G quotient of Y, and again, a point. Okay. And in order to realize this guy, I have to choose therefore some partial compactification of some orbit. And I will take, since this is related to n, the orbit will be G mod n. Partial compactification will be affine closure. This guy is quasi-affine, it's open in its affinization. And so I can use this. And I can use this construction. Okay. So what can I say? Well, in general, what one can say about this construction is that that this is a submoduli of the loop Grassmannian, and it is closed. And how do you see this? Well, such data mean that one has some G torsor P over the curve, and since we are in the, well, and there is a trivialization in other words, a section tau on U, sorry, on C minus D, if I'm looking at the phi bet D, and then they should have some compatibility, or some extra property. I mean, this is just the usual data for a loop Grassmannian. But now the extra property that will describe this part here is that if I take the section and I multiply it with the group A. So this lies in the torsor. So this is a reduction to A of the torsor on U. And now I ask that it extends to a section on X of twisted Y. So by twisted Y, I will mean the following thing, that I will multiply this to, Y. It's a G space, I multiply and I divide by diagonally here. And then you can see that this guy contains G mod A twisted. I said that Y contains such an orbit. And what this thing is, it's essentially just this quotient. And this quotient has section A tau, which is a section on U. Okay. And so now we can ask that this section, that this A tau, which is a section on U of this subspace, that it extends, but of U it may fall off the open orbit into some boundary. Okay. And so so the G, it was a G space and it contains an open dense orbit. And so there is some point here and there is the stabilizer of the point. So this is the orbit. Okay. And so this is how this A appears. Okay. So it depends on the size of the orbit. So just by basic manipulations with just definitions of maps between stakes, between the quotient stake and the scheme and the quotient stake, we get a description like this. And then one finds that S0 bar looks like this. So it is some kind of moduli of maps into this G quotient of G mod n affinization, comma, point. Okay. And so this is therefore a classifying space for this guy. And one can do similarly for other relevant, interesting subspecies of the loop Grassmannian. For instance, well, one can, okay, so let me describe a union of closures of all orbits. So you can think of this as some kind of a, so it's a disjoint union, so it encodes some kind of filtration of the loop Grassmannian. And this is again of this nature, except that the group G is replaced by a larger group, so it's called the Wimberg group of G. So this is G times H divided by with a center. So here, actually, G should be maybe simply connected for the standard definition of the Wimberg group. And so one still has this space, but one has another group. And one can find what this component of this moduli is by remembering that the Wimberg group goes to the adjoint quotient of the Cartan, and then one pushes objects to the Grassmannian of the Cartan, and this contains points indexed by lambdas. So in this way, one lambda defines a part of this moduli, which is this S lambda bar. And similarly, one can do for closures of G lambdas. So let's see, it's, again, I need a Wimberg group, but now I will need the Wimberg semigroup. So what is a Wimberg semigroup? So it contains this group, and it can be defined, for instance, as endomorphisms of G mod n affinization with respect to the Cartan, which acts on the right here. Okay. Or it can be defined in terms of wonderful compactification. So it is the affinization of some torsor Q over the wonderful compactification of the adjoint group. Okay, and so this construction then gives, well, this was not quite right. I will need to take a reduced part here, and again, I will just need somehow to specialize to lambda by going from V to the adjoint Cartan in the Grassmannian of the adjoint Cartan. Okay, and so so now that one has classifying spaces for these basic quantities, like these guys, all of these guys, those, then one can take classifying spaces for intersections. So the example will be S alpha minus, so let me put alpha here and 0 here, sorry, and 0 here, and minus direction here, and the closure here. And so again, I want to interpret this in terms of some kind of a classifying space. How do I find a classifying space? Since these are intersections, I just need to take maps again into a new classifying space, which is a fibered product of classifying spaces for these two guys. And then what we will get is G mod n affinization times G mod n minus affinization divided by a Cartan and divided by the group diagonally. And now one has some kind of finite dimensional description in terms of these classifying spaces, and one does not have to think of the loop Grassmannian at all in order to calculate these guys by this mapping prescription. Okay, and so the last part was the comparison of two kinds of Zastava spaces. And so this comparison is that, say, when m is equal to 1, and when q is, well, one can think of it as a quadratic form, and it should be the fundamental level for a group G. And here I should be the set of simple roots. And maybe for simplicity, I will again think that this is simply connected. So in this case, all these constructions of Zastava spaces and loop Grassmannians and this S0 bar, the closure of the semi-infinite variety, will just coincide for this data IQ and for the reductive group. And if you allow any m, then and keep q as above, then one will get some kind of a new space which will function very much like the loop Grassmannian. So when m equals 1, then this is equal to the loop Grassmannian of the group. So on the loop Grassmannian of the group, one can realize, say, the dual of basic representation by sections of the fundamental line bundle. Okay. And this realization has some various miraculous properties, so nice properties, familiar in the theory of integrable representations of affine groups. For instance, the sections on the loop Grassmannian of this line bundle restrict isomorphically to sections of the same line bundle, but just on a Grassmannian of a Cartan. And this is a basis of the Katz description of basic representation in terms of vertex operators. And there are other properties, like one can describe this basic representation as a large product of C2, some kind of semi-infinite tensor product. And so all these miraculous properties of the basic representation will extend to representations of level m, provided that one localizes line bundle not here, but here. So the following will be true, that if I take loop Grassmannian and sections on sections at level M. These will be the same as sections on this mth version of some line bundle, of some basic line bundle. And then the geometry of this guy, the same as the geometry of this guy, will endow this representation with various properties in the same way. So one cannot, for higher M, one cannot see such things here, but one can see them here. And okay, so that's about it, yes.